Hi viewers, welcome to my class on mechanics of materials. In today's class, I'll be working out a numerical example on the deformation of a step bar, change in length of a step bar. In the figure, a step bar is shown. Question is to find out the stresses induced in and the total change in length of the step bar shown. The Young's modulus of the material is 200 gigapascal. So you need to find out the stresses induced in individual sections. There are only two sections. Under the action of this load 34 kilonewton, you need to find out the stress induced in this section and the last section. So here the dimensions of the bar is given. The cross section is circular because it's 60 mm. Phi stands for diameter. So first section is having a dimension of 60 mm diameter, and the second section is having 50 mm diameter. So in this case it is subjected to a pull 34 kilonewton at the end, and also an intermediate load is there 60 kilonewton. It is pulling towards right. So it is applied here. Now one force is acting at the end 34 kilonewton. It is pulling the stepped bar at the end, and also another force is acting at the junction here, and it is 60 kilonewton. Again it is pulling towards right. Now considering the equilibrium of this step bar, there should be an opposing force because both the forces are acting towards right. There should be an opposing force to maintain equilibrium. This fixed end has to exert an opposing force to maintain equilibrium. So from statics we know that summation of forces should be equal to 0 in any direction for equilibrium. So if you sum up the forces, if you assume a reaction here, the summation of the forces should be equal to 0. So 60 plus 34, if you are taking the force towards right, plus this reaction is equal to 0. So 60 plus 34 plus reaction, if you take it towards right, plus R is equal to 0, and you get R as minus 94. 60 plus 34 will get 94. 94 minus indicates it's not in towards right, it is towards left. So the force will be acting like this, and the fixed end will be exerting a force towards left. I'll explain this with the help of next figure. Now 60 is acting towards right, 34 is acting towards the right, and now if I take R towards left, you will get 60 plus 34 minus R is equal to 0, or directly R you will get as 60 plus 34 or 94. Okay, so you can see that if R is 94, it will be balanced. 94 is acting, the fixed end is exerting 94 kilonewton, and there is a rightward force 60 plus 34 94, and that will maintain equilibrium, and the summation of forces will be equal to 0. Now the question is to find out the load in individual sections. There are two sections. We need to find out the load acting. What is the load acting in the first section and what is the load acting in the second section. To reveal the internal forces in each section, you can take a section in that which section you require the internal force. You take a section plane there, consider the right portion or left portion. So I have shown the right portion. Okay, so I am taking a section here, consider this right portion. So that sketch is shown here. Now when you are considering this portion, for maintaining equilibrium there should be an internal force. So that internal force I have shown here by P1. So we need to find out the internal force acting in this first section. Okay, so when you consider the free body diagram of this, the internal force I shown it towards left. Since it is both the forces are acting towards right, this should be towards left. So you can find out P1 as 60 plus 34. Even otherwise you can find out, take simply a section, you forget about the direction, you just add up these forces. 60 plus 34, because 60 is towards right, take towards right as positive. 60 plus and this is also towards right, so 60 plus 34, 94. So you get P1 as 94. So you need not even assign the direction. Take a section plane here, add the forces on the right side. Okay, this is a section plane. Consider all forces on right side of that section plane and add the forces by taking the force acting towards right as positive. And okay, so this is positive, this is positive. So 60 plus 34, 94. So when you are getting 94 positive value, that means a pull is acting or tensile force is acting. It is subjected to tensile force. Similarly, in the second section, you take a section, consider only the right side, whatever forces are there you consider. So you have only one force and it is acting towards right, so you can take it as positive. Acting towards right means it's a pull. I am giving in a simplified way to calculate it. So when it is acting towards right, you can consider as positive, and so that means 34 kilonewton, 34 into 10 raised to 3 newton. And it is once again positive means it's tensile force. So this is the easiest way to find out the internal forces in each section. After knowing the force in both the sections, you can find out the stress induced in both the sections. Stress is load divided by area, or resisting force divided by resisting area. Resisting force in the first section we identified as 94 kilonewton. It is 94 into 10 raised to 3 newton, converted kilonewton into newton. The area, since it is a diameter is given, area of cross section is pi by 4 into diameter square. Diameter of the first section 60 mm. So pi by 4 into diameter square, which will give the stress as 33.246 Newton per mm square. Similarly, the stress in the second section is P2 divided by A2. So the internal force in that section P2 is 34 kilonewton, 34 into 10 raised to 3 newton, conversion from kilonewton to newton. And the area, since the diameter is 50 mm, pi by 4 into 50 square, which will give the stress as 17.316 Newton per mm square. Now to find out the deformation, in this case again elongation, both the sections are elongating, so delta L1 is P1 L1 divided by A1 E1. So P1 is 94 into 10 raised to 3, that force in that section. Length of that first section is 200 mm. Okay, 200 mm. Area of cross section pi by 4 into diameter square, and Young's modulus, it is 200 gigapascal is given. No, gigapascal conversion to Newton per mm square is 200 into 10 raised to 3 Newton per mm square. So 200 into 10 raised to 3 means 2 into 10 raised to 5. So 2 into 10 raised to 5 Newton per mm square. So will give the elongation in that first portion as 0.0332 mm. Now elongation of the second section is P2L2 divided by A2E2. P2 is 34 into 10 raised to 3. The length of that portion is 150 mm, and diameter you know, so you can find out the area as pi by 4 into diameter square into Young's modulus is 2 into 10 raised to 5, which will give the deformation or elongation as 0.013 mm. Now you can add both the elongation, which will give the total change in length. So total change in length is delta L1 0.0332 plus 0.013 is equal to 0.0462 mm. So this is the total increasing length of the step bar under the action of these forces. That's all for today. Thank you for watching.